Hi everyone, welcome to another machine learning tutorial. In this video, we are going to look at how to implement a genetic algorithm from scratch with Python and perform a feature selection task. So let's get started. So first of all, for those who are beginners, I have some links in the description that you can use to introduce yourself to feature selection and machine learning for that matter. So let's proceed. So the Python notebook I'm using is available on my GitHub repo, so you can just get them. So the link to the GitHub repo is in the description box. So you can find that here. This is the GitHub repo. I think I'll just refresh this page so that we see it here. I'll just do it here. So I have a couple of notebooks that you can use. So just feel free to use them and then get started. So let's see. Yeah, they should be here. I think it's about it. So let's just, that's about it. So let's just look at how it's done. Okay, so just get the link and then download this notebook. You can also use Google Colab to open the notebook directly from GitHub. So I have tutorials that show how to do that as well. All right, so let's do a quick recap of genetic algorithms first before we start this. So I will shift to a slide presentation that I have so that we can all see it. So with genetic algorithms, it's an optimization algorithm that mimics the evolutionary process in living organisms to identify optimal feature subsets. So we apply a series of evolutionary operators to explore the feature space and select the optimal or the near optimal subsets for our model preparation. It uses a random set. That is the classical genetic algorithm, but there are improvements that have been made, which I'll talk about later. So this is an overview that you can use to get started. So we input our data, we initialize the population, compute fitness, and then we go through selection, crossover, mutation. We go through for a couple of times until a stopping criteria is met. Then we select the best subset so far, and then we use that for our model preparation. That's just about the genetic algorithm, but you can check the links in the description box to learn more about genetic algorithms as a whole. All right, so let's proceed. So with the genetic algorithms, it's important we also look at something first, which I will talk about, and that is the representation. It's very, very important. So we represent the genetic algorithm with this structure here, which represents a chromosome. That's what it's commonly referred to, a chromosome. So if, let's say, your entire data set, it's about 5 features, then we represent it with this binary bit here, which is 5. Okay. And then what we have is that for each of the feature, if it's selected, then we represent that particular section, which we call gen. Okay, that portion we call gen. We specify 1, and the feature has not been selected, it's 0. So here it's a total of 5 features in the data. However, 3 of these features have been selected. So you have the first, second, and then the 5th feature. And so that's how it is. So what happens is that these bits get continuously flipped because of the evolutionary operator that we add, and then at the end of the day, we get the one that finally gives us the best subset. Now, as we are doing this flipping, okay, we have several of these chromosomes which are initialized using this. So we have P, that's population, X1, S2, S3. These are representing, each of them represents a chromosome until the N, which is the population size, which has been defined here. So for each of these, what happens is, because this approach is a wrapper-based approach, whenever we do the selection, for example, this, we evaluate using a classifier. Okay, so once we evaluate that classifier, that becomes the fitness, and then we evaluate other chromosomes as well continuously until we get the expected result, until we meet the stopping criteria. That's basically about how it operates. All right, so enough of the beginner talk. Let's actually go to the Python environment and then start looking at the implementation, which I have done here. So if we look at several tutorials, there will be several variants, but the concept still remains the same. Here I'm using Python, and so I need my libraries, which I'll need to first import. Okay, I also believe that I have already downloaded the notebook, which is here, and then you are following. So these are libraries I'm going to use. And so because it's a Jupyter notebook, I need to first import them. And then these are functions. So I have one here, several of them. So each of these functions perform a task. So it's important for me to explain these for you as well. Now, I first have to import my data. So I have a function that allows me to import the data and then prepare it into a format that we can feed into the genetic algorithm. So this is the function that's that. So I'll basically input some files. I have train file, test file, val file. Now in machine learning, we have these different data that we use. We have training file for training phase, and then test file, validation file. So for the genetic algorithm, we are now using it to select the subset of feature that we want. And therefore, we need to have files to start with. And then once we are done, and then we have our final subset, we test with an independent data set. And that is what we have as the test file. So the train file, the val file, these are used for the initial feature selection or optimization. And then once we have the subsets, then we now test with this independent data set, which is the test file. That's basically about it. So here, all I'm doing is reading the files and then putting them into a NumPy array. Then I'll return them. That's basically what is happening here. Now, for a detailed explanation, you can also book a one-on-one session with me. All right. Now, in the genetic algorithm, the first stage is to generate your population. And so this function here allows me to do that. And so here, what I'm doing is to randomly select the features. So I'm using NumPy random.random. That's what I'm using to select. Now, because these are bits 0 and 1, that is why I have these two here. So either 0 or 1 will be selected for a certain number of times, and then the dimension. So this will now give me the array, the NumPy array that I want, and then I start the process. After that, we go to selection. So selection here, we are selecting some individuals for reproduction. Among the population that we have, we are selecting some individuals which we will now apply the other evolutionary operators on to hopefully generate an optimal or close to optimal subset. So we need to first select them. And for selection schemes, we have several of them. Here I'm using the tournament selection. So it's important we also look at what the tournament selection. I have a page here that shows it's here. So there's an image, and I'll leave this link also in the description box. So with tournament selection, what we are actually doing, okay, that we are going to select some individuals for reproduction, and we do that with tournament. So what we are doing, we are going to select some individuals. We choose them at random, and the one with the best fitness. So in this case, the best fitness will be maybe a predictive score on some other measurements. All right. So we select among the individuals we have selected, the one with the largest fitness or the highest fitness is selected for further reproduction. So we do this tournament a number of times until we get the expected individuals that we want selected. That's what basically it is. So this is just one example of them. So we are selecting K chromosomes at random. So here we have A, E, and then T. And so the best or the fittest, if it's A, then we select that one. So this becomes the selection. All right. And then we do this for several number of times, which we can find that in the code later on. But this function allows us to always call this and then perform the tournament selection. Okay, so that's basically what we have here. And then after selecting the individuals, we also look at a crossover operator. So with crossover, what we are doing is we are exchanging genetic information. That's what we are doing here. Let me shift to this slide for us to see what the crossover looks like. So with crossover, we randomly select a point, and then the left and the right side of that point for both individuals. We deal with two individuals here. We exchange their genetic material, their genes. So if this is the point, then what happens is that in both parents, one point from the other gets into the other point of that the other parent, and then the other parent also transfers its genes from that particular region, okay, to the other parents, and then we form two offsprings or two children. And this is what is demonstrated here. So here we see that this parent 1, parent 2, and then when we come here, we see that in the first offspring, it maintains the first half of parent 1, and then it acquires the second half of parent 2, which is this one here. You can see it here. And then the second offspring maintains the first half of parent 2, which is here. And then it acquires or inherits the second half of parent 1, which is here. So this is what a crossover does. So we are exchanging genetic material. So we have that exchange. So here, this goes here, this comes here. That's what we see in the offsprings. So this is what crossover does. Right. So once we have the crossover done, we apply another operator, which is mutation on the offsprings. All right. So let me actually go back. So with crossover, the points that we use, okay, it's typically randomly selected. That is for the classical genetic algorithm. It's randomly selected. All right. But there are other approaches which use guided search or other heuristics. These are things that we can talk about later. But the point is for you to understand what the crossover does. All right. And after that, we go to mutation where certain points are randomly flipped. So we have bits 1 and 0. So if the point selected is 1, the position, then if you are doing the mutation, it gets flipped to 0. So 1 here means selected. If it gets flipped to 0, that means that that feature has been dropped. All right. So it's not only for 1, but you can also have 0 to 1, as we can see from here. So that is mutation. So we do the flipping, and that gives us mutants. So these also become other offsprings that we have, in addition to the other offsprings from crossover. So that's what we have here. So these are the evolution operators that we use in genetic algorithms. And then we now evaluate them, pick the best, go through another round of selection, crossover, etc., until we get what we want. So the function for mutation is also here. And also for the mutation the mutation point is also random in the classical one. Of course, there are others that use a guided approach. These are things that we can talk about later. So these are used to improve the genetic algorithm. And so for now, we are doing the basics. That's what we have here. Now, once we have the offsprings generated, of course, we also need to evaluate their fitness. Now, because this is a wrapper approach where we are including a classifier, we need to have some form of predictive performance. And so that's what this function does for us. So we train the model with the selected features. We evaluate here. I'm using the F1 score. You know, F1 score is actually useful when you have an imbalanced data set, and it also works for multi-class. So that's why I chose this one. So you need to also check what metrics are being used or commonly used in the field or recommended, and then you can use that one. So there are other ways to also do the fitness. We have those that use the Pareto font, etc. But these are things we can talk about later. And then the main algorithm here, which first initializes the population. We have it here. Then we create our classifier. We evaluate the initial population. Then we go through selection, crossover, mutation. We get the best for that particular iteration, and then we go over again. Now here, I'm doing several rounds of this. So that's why we have this iter here, indicating the number of iterations. So we do a first round, then we go again another round. We do it until the number of iterations are reached. So that becomes my stopping criteria or stop criteria. That's basically what it does. And this function here, before we call it, we need to supply all our information. So we have train file, test file, val file, number of iteration, population size, R cross, R mute. So these are parameters you set, the crossover rate and then the mutation rate. I will talk more about them in another video. So these parameters, you need to set them before you run your genetic algorithm, right? So this function is also there. I think I'll just rerun them so that we see. So we are just going to run them. Yeah. And once we run them, then we now set them. So here, when I come here, I'll need to run the algorithm. However, I need to get the data set that I want. And here I'm using the Wisconsin data set, which I've also prepared here. It should be somewhere here in my GitHub repo. I think I will shift to this one. Yeah, it's here. So Wisconsin data set, this one here. Let me just shift back again. So I have, yeah, so Wisconsin, yeah, this one here. Now, take note that I've already done the pre-processing. So if you want the original data set, it's here. So this is the original data set from the UCI machine learning repository. So here I'm loading it straight from my GitHub repo. And that's why I have what the data part here. That's my GitHub repo. So instead of downloading them, you can just read the file directly from a remote web server if you have the address, the download address. All right. And then I set the path for the training, test, and validation files. Then I set the parameters. So these parameters, it's important to know that there is nothing like a gold standard. So usually you have to check the literature to find out what parameters are appropriate or are recommended for your data set or your domain. It's always important to do these things. And then finally, you run the algorithm. So here I'm setting the iteration to, I'll set it to 10, and then we can run it. Let's see. So if I run it, it will read the files and it will start the iteration. So when it does iteration, after each iteration here, the best discovery so far is indicated, and then it gives us the score as well as the number of features that was selected. So we have a total of 30 features. It should be here. Yeah, so the point is select a subset that will be able to give us a good relative performance. So typically with feature selection, sometimes you can have several features. I think I'll open the data here. We can have several features, and some of these features may not carry any meaningful information. Some too may be redundant, and all these things will add to the computational cost. It will waste time, and it might actually sometimes negatively impact the model performance. So when we do the feature selection, we are selecting the subsets that is very relevant and actually useful, and then can actually help us to get a better model. And once we do that, it also saves us time, especially when dealing with a production environment. So these are measurements that have been done for different patients. All right. So instead of now going to do all these measurements again, which will be expensive, if you know that measurement variable A, variable B, variable C, D, these are the most important, then when we have the patients or individuals, we just measure these variables or predictors, and then we use that to do the prediction or the diagnosis. That's basically what feature selection helps us to do. So take note of that. So there's a wrapper. We are dealing with a machine learning model. So we have our variables, which are the features, or in genetic algorithms, we will say each of them represents a gene. Then we have a class. This is the output, the label. Then put it that way. So label here, I use 1, 0. The original one is supposed to be malignant, then benign. However, the machine learning models do not understand this text and this text. So a way to make the models understand the labels is to encode them as integer values. And that's what I've done here with 1 and 0. So this is also just by the way. Now let's get back to Python and see what has been done. Okay, good. So now we see the optimization process. It goes on for some time. And then we see that it says what? After the 10th iteration, we get what? A subset of 13 features. Once we have that, we test on an independent dataset, which is the test dataset, and that gives us 0.877. By the training phase, we got 0.90. And there could be a number of factors. So typically, what you can do is to run this for several iterations, and then you'll be able to get a very good result. Now, this one, the difference is not that much, so I will consider it. However, if after training phase, the score you have and the one that you have after testing on a test data set is too wide, then there could be a problem. So it's something you can also check later on. But of course, now let's assume everything is okay. So once you have this, then you can now proceed with the next phase of your task, whether you are building a model or whether you are looking to interpret it, or whether you have some other tasks you want to do with the subset. That one, it depends on your study plan, your research plan, or whatever plan you have. So this is to help you get started to get that subset of features, then you can proceed with your decision making. Okay. You can also try with the Parkinson's. Here it's 754 features, which is a lot. And so that's where you now actually appreciate the optimization process, because what we can do is to run it for several iterations and see the best optimal results that you have. So it will drastically reduce. As a matter of fact, even this one, it's 30, but then what we have is 13, which has actually reduced by 50%. So which is very, very good. So that's in a nutshell how we use genetic algorithms to perform feature selection, but there are other things you can also do. Now, with genetic algorithms, it's important to note that they have some drawbacks, which I will share right now. One of them is that it has a higher computational cost. It's random search, and so you have to do several rounds of iterations before you can get a good result. You also need to tune the parameters, which can be demanding, and it also shows it lacks diversity. Also susceptible to local outmark trap, and you can also have premature convergence. Now, there are ways to handle this. So there are those that use the strategy of parasearch to try and do deep search. There are also those that tune the parameters. There are those that will use immigration. You also have those that use adaptive techniques on mutation, crossover, immigration. Maybe they also use probability based. So these are things you can use to improve. But I have codes that are also improved using some of these techniques. So for those who want those codes to, you can just check the description box or just contact me if you want some improved version as well. So I think that's all for this tutorial, and I'll see you with another tutorial later. Bye.